So in this lecture we shall be analyzing the voltages and currents in three-phase systems, star connected and delta connected. But before that, just have a quick recap of what we studied yesterday in our previous lecture. So in the previous lecture we talked about the sinusoid waves that are being generated in multi-phase systems like two-phase and three-phase, and the type of connections like star and delta, where star comprises of 4-wire and delta comprises of 3-wire connection. Then we move on talking about how this sinusoidal waves are generated in single phase and two-phase and three-phase. Then we further talked about the Phasor representation of the sinusoidal waveforms, which in case of balanced system are distributed over or are displaced by 120 degrees. Then further we came up with the voltages, the voltage values for each waveforms, which were represented by the expressions Vp angle 0 for VAN. VBN corresponded to the voltage for phase B, which was displaced by an angle of minus 120 degree but have the same magnitude as VAN. Likewise, VCN has the same magnitude but is displaced by an angle of minus 120 degree from the reference 0 or plus 120 degree if you talk about the clockwise rotation. So minus 240 corresponded to anti-clockwise rotation, while plus 120 corresponded to the clockwise rotation, and this type of sequence is termed as ABC sequence or positive sequence. Then we talked about ACB sequence or negative sequence. So one thing that sequence is always kept in mind is this is very important, because things that we see in DC supplies. So whenever we connect batteries in series or parallel, we always talk about the polarities of the terminals of the battery, because depending upon what polarity, how we are going to connect the polarities of the battery would be connected either in series or parallel. Likewise, when we deal with three-phase system, so we always talk about the sequences in order for a three-phase system to be connected to another three-phase having same magnitude. So this means that if we are given a sequence of ABC of a three-phase system, then that three-phase system can only be connected to another three-phase system having the same sequence ABC. So if ABC sequence is connected to ACB sequence of another phase, then that may result into catastrophic fault. So there was a slight correction in our previous lecture, that the sequence VAN, VBN, VCN corresponded to the phasor shown here. So in the previous lecture we switched these phasors. So this is the correct phasor representation of the sequence here. Since VBN is lagging by an angle of minus 120 degree, which means that this phasor would be represented clockwise by an angle of 120 degrees. So VBN in this case is lagging VAN by 120 degrees, and VCN is lagging by an angle of 240 degrees. So this is what we have written, VCN equal to VP minus 240 degrees. So any phasor which comes anti-clockwise before the reference phasor is said to be leading, and that is why if you look into this figure, so you can say that VCN is lagging by VAN by an angle of minus 240 degrees, or is leading VAN by an angle of plus 120 degree, and that is what we mean by writing this expression. So this expression means that VP angle 120 degree is a phasor which leads VP angle 0 by an angle of plus 120 degree. So VCN can be written in either ways. Likewise, for the ACB sequence or negative sequence, we have VP angle 0 as the reference, and VBN either leads VAN by an angle of plus 120 degree or lags by 240 degrees. So VBN is written as VP minus 240, VP plus 120 degrees. So this is a slight correction that should be incorporated in our previous lecture. Then we came up with the conclusion that if we sum up all the three phase voltages VAN, VBN and VCN, so what we get is 0 in case of balanced supply, balanced three-phase system. Now today in this lecture I shall be talking about the relation between the phase voltages and the currents. So starting with the star connected system. So let us assume that we are given a star connected system. Let's say this is the phase 1, then we have phase 2 and the third phase. And as I told you that we connect the same terminals of all the phases together in a star connected system. So if this is momentarily minus and this is plus, then this will be minus at the same moment, and this will be minus and this will be plus in the same moment. We call this line, since in case of a star connected system we have 4 wire, so we had a common point called as neutral. So this was represented as N, and let's say this is terminal A corresponding to the phase A, then this is B for phase B, and this is C for phase C. So this is a star connected system. And now one thing more, that we talked the names of the phase as A, B, C, and they can also be represented in terms of R, Y, B. So R, Y, B is in common nomenclature that you will observe in power system. So where R stands for red, Y stands for yellow, and B stands for blue. So in case of three-phase systems, we normally represent the phases by R, Y, B in industries. Now there are few terms that are associated with three-phase system, like line voltage and phase voltages. So line voltages are the voltages that occur between two line or two terminals. For example, if I talk about the voltage between terminal A and B, let me draw this. So if I am talking about the voltage between these 2 points, then this voltage is termed as the line voltage, and we abbreviate it, for example, as VAB. So let write the things in small letters, because small letters would be representing the instantaneous values. So the potential between this terminal and the terminal B, A and B, is nothing but what we call as the line voltage. And the voltage that occurs between the terminal A and that of the neutral, so the potential difference between A and neutral is termed as the phase voltage. So this is the phase voltage. Likewise we can have, so let me write all the line voltages which are existent in this system separately. So the line voltages are VAB, VBC and VBC and VCA. So these are the line voltages that exist within the three-phase system. Then we have phase voltages as VAN, VBN and VCN. So these are the phase voltages, and then we have line voltages. Likewise we have currents that flows through the line as well as phase. So the current that flows through phase, let's say this phase is IAN. Well, let's talk about current later on. First we deal with voltages, then we'll come to currents. So now we are interested to find the relation that exists between line voltages and phase voltages. So there are many methods that you can adopt and come with the relations between them, but we will normally prefer Phasor representation because this is the simplest form or easiest form. So before drawing the Phasor representation, well, let's draw it first. So we represented the phase voltages VAN, VBN, VCN in our previous lecture by phasors as shown here. So this was taken as VAN and displaced by this phase was the phase voltage VBN at an angle of 120 degrees. So let's say this is VBN, and this was displaced by an angle of 120 degree. Then again VCN was displaced by 120 degree. So this is VCN. So they are all displaced by 120 degrees. Now if I look into this particular figure, we are talking about the line voltage. So line voltage is the voltage that exists between phase A and B. So in order to apply KVL, and of course VAB means that we are talking about the voltage of phase A with respect to B. So which means if this is phase A, so we are going to take this as positive and this as negative. And if we apply KVL to this particular loop, so we are trying to find the voltage VAB. So this is the loop we are interested to apply KVL in. So if we apply KVL in this particular loop, we have minus here, plus here. So applying KVL, so let me simply write this as KVL. So if we start from this point, from minus to plus, we have VAB. Then at this terminal we have plus, and this is minus, and the potential that exists across this particular source is VAN. So we have minus VAN, and again minus to plus is plus VBN equal to 0. So VAB can be written as VAN minus VBN. So this is a relation. Let's say this is equation 1. Let us encapsulate this. We call this equation as 1. What this relation says is VAB is the line voltage, VAN, VBN are the phase voltages. So if you look into the phasors, so we made a mistake again here. So this is VCN. Since VCN lags voltage VAN by an angle of 240 degrees and VBN lags by an angle of 120 degrees. So if you look into the phasor representation, so VAN, we have VAB as the line voltage, which is VAN minus VBN. So this is plus VBN, and minus VBN will be the phasor in the opposite direction of same magnitude. So this is minus VBN. The angle between minus VBN and VAN, it should be how much? So since this angle from minus VBN to plus VBN is 180 degree, while this angle is 120 degrees, so the angle that we are left with is 60 degrees. So the angle that exists between VAN and minus VBN is 60 degrees, and now we are interested to find the line voltage VAB, which is a resultant of these two phasors VAN and minus VBN. So let's find the resultant. So one thing is for sure, since the magnitude of VBN and VAN are equal, and thus the resultant will be exactly in the center of these two phasors, and thus will be making an angle of 30 degree. So this is VAB, which is equal to VAN minus VBN. Likewise, we can talk about other line voltages like VBC and VCA. So I'll be writing these line voltages after I come up with the expression for VAB. So let us first write the line voltage values of line voltages of the other remaining terminals as well. So we are left with VBC and VCA. So VBC, again applying KVL to the loop, which comprises of two terminals B and C. So VBC taking this terminal as positive and C as negative. So VBC can be written as VBN minus VCN, and likewise, so we can call this equation as 2. Likewise, we have VCA as VCN minus VAN. This becomes equation 3. So these are the relations between the line voltages and phase voltages, the equations that represents the relation between line voltage and phase voltages. Similarly, VBC can be represented on phasor diagram. So since VBC is VBN minus VCN, so if we draw the phasor corresponding to VC minus VCN, which will be negative in this side, and the resultant of these two phasors will be, that would be somewhere here, and let's say this is VBC. Likewise, VCA, which is the resultant of phasors VCN and minus VAN. So minus VAN is somewhere here, and the resultant of minus VAN and VCN is the phasor of VCA, line voltage. So this in fact is the phasor representation of the three-phase system, representing the phase voltages as well as line voltages. So these are the line voltages, and the remaining represents the phase voltages. These are the phase voltages. So now after obtaining the relations that represents the equations that will represent the relation between line and phase voltages, we will finally come to a representation of these, or the values of the line voltages in terms of phase voltages. So let us talk in terms of the magnitude. So let me redraw the phasor diagram. So for only, if this is VAN and this was V minus VBN, or let's say we only talk in terms of magnitude, we'll try to find the resultant of the phasors. So if say that we have the magnitude of VAN as, let's call VAN, or let's represent this in terms of RMS value. So we'll try to find the value, the magnitude of the resultant in terms of RMS. So the RMS value of VAN will be equal to V minus VBN or VBN. We are talking only of magnitude, not of direction or sign. And let's take the RMS value of these voltages. Since these represents the phase voltage, let's call this as VP. VP is the phase voltage. So we have VP here and VP here, since the magnitude of both the voltages are same, and as I told you that we are talking about the balanced supply, balanced three-phase systems, and this angle is 30 degrees. So in order to obtain VAB, which is what the magnitude of this, the RMS value of VAB is taken as VL, the line voltage. So the resultant of this phasor can be represented as VAB or VL will be equal to under root VAN square or VP square plus VBN square, again VP square, plus 2 VAB VAN, 2 into VAN and VBN cos of angle that exists between them, which is 60 degrees. So this is a shorthand method to find the resultant of phasors, and you must be aware of this formula, and if you don't know, you can find the components and you will come with the magnitude of VAB by this expression. So if you further solve this, then VAB, which is line voltage VL, can be represented as, further simplifying this gives us, so this is 2 VP square, then again 2 VP square, and we are left with 2 VP square 1 plus cos of 60 degrees. And on further simplifying, we get VL as, So under root 2 into 1 plus cos 60 degree gives us a value 3. So we are left with root 3 and taking Vp square out of the root sign, so we get Vp. So this is the relation between the line voltage and the phase voltage in case of a three-phase system. So if you try to find the voltage values for other phases as well, like VBN, VCN, so we'll come with the same relation which exists here. Now this can be represented in terms of phasors as well. So this is the magnitude of the RMS value of the line voltage. So since we saw in our phasor representation, let me show that again. We saw that VAB leads VAN by an angle of 30 degree. Likewise, VCA leads VAN by an angle of 120 plus 30 degree, which is 150 degrees. And VBC leads VAN by an angle of 240 plus 30 degrees, which is 270 degrees. So after obtaining the magnitude, we can straightforward write that VAB has an RMS value root 3 times of phase angle 30 degrees leading by the reference. VBC will be having the same magnitude, as well as VCA will also have the same magnitude, and the angle each of these will be having. So since in the phasor diagram we saw that VBC, let me show that again. So VBC is what? VBC is 240 plus 30 degrees leading by VAN. So this can be written as 270 degrees, and VCA was leading by an angle of 120 plus 30 degrees, which is 150 degrees. So this is the representation of the line voltages corresponding to VAB, VBC and VCA that we obtain through the phasor representation. And one thing more, if I remember correctly, I yesterday told that VP is the peak voltage. In fact, that was phase voltage, not peak voltage. So VP that was talked about in the previous lecture was the phase voltages. So these are the line voltages that we came up with of the three-phase systems. And likewise for the line currents, if you look into the original figure that we have here, so let me rub this all. So for line currents, what we have here is the current that flows through the phases. So let us call these currents as IP. So the current that flows from neutral to terminal A is IP, and the current that flows outward from terminal A is IL. So P stands for phase, L stands for line. And since we see that at this particular node A, since there is no another path for the current to flow, and thus the current that comes out from neutral moves towards A, has only one path, that is the line through which it has to flow, which means that IL in case of star connected system will be equal to IP, which is line current is always equal to phase current in case of star connected three phase systems. So this holds for all the phases. So the phase current that flows through each of these phases will go through their respective lines. And the phase angle these currents make with the reference VAN depends upon the load through which they have the loads which are connected to the three phase system. So whatever load we are going to connect here, ZL in the three phase system, will decide the angle of the current IL. So that depends upon the problem that we are given. So if, we'll have to know the value of load in order to find that how much current lags or leads by the voltage. So that can easily be obtained by the expression IL equal to V line voltage divided by the load. So whatever load is connected between the line through which the current is to be obtained. So the angle of this particular component of this load will decide the angle of the current IL it makes from the phase reference phase voltage VAN. Now talking about the delta connected system. So in case of a delta connected system, that as we saw yesterday, we'll be having the three sources connected in this fashion. Where this is VA. Since we don't have neutral in these cases, so we'll be representing, if this is terminal A, this is B. So the voltage that exists between these two terminals will be VAB. This is plus, this is minus, and the minus terminal of VAB will be connected here to the plus here and minus here, then plus here and minus here, and this is terminal C. And this voltage is VBC, while this is VCA. And from each of these terminals we'll be having the outputs. So since this is a three wire system, so we'll be having three wires. And now we will try to find the relation that exists between phase and line voltages as well as current. So if you look into this figure, the line voltage is the voltage that exists between this point and or this line and this line. So let's call this as VL, the line voltage, while the phase voltage is the voltage that exists between or that exists across one source, which is VAB. So VAB is the phase voltage. And in fact, if you see that terminal B is at the same potential as this particular point, as well as terminal A is at the same potential as this point, which means that in the delta connected system we have the line voltage here equal to the phase voltage, talking in terms of RMS values. And phase voltage is VAB. Likewise, this relation will hold for all other three phases. So we'll be having, if you try to obtain the relation, try to obtain the voltage that exists between VBC, that will again be the line voltage between these 2 points, and which will be equal to the voltage that appears across the second source VBC. So this means that for a delta connected system, we'll always be having VL equal to VP. Now if we talk about the current, so in order to find the current, we'll have to connect loads across the voltages. So if suppose we have again delta connected load, Now if we see that this is the phase current IP while this is the line current, so let us call these terminals again as A, this is B, and this is terminal C. So instead of calling this as IP, let us call this current as IAB. And this current is IBC, and this current is ICA. So we see that the line current that comes from these line will be divided into two currents, IAB and ICA. So this can be written as let's say we'll write this current IL simply as IA, since this flows through the terminal A, and IA can be written as IBC minus ICA. And the similar relations could be found for the other currents that flow through the terminals B as well as C. And now again, if we see that this is a balanced load situation where the load are all connected in balanced condition, then the magnitude for IBC and ICA will be equal, but they will be displaced by an angle of 120 degrees. So let for the time being consider that IL or IAB, since the voltage that exists between terminal AB is VAB, and depending upon what load is connected between these terminals, IAB will be either leading or lagging VAB. So for the time being, let us displace it by an angle of theta. So if this represents the reference axis across which we are taking the phasor for VAB, and let's say by an angle of theta, IAB is displaced, let's say this is angle theta or phi, then IBC will be lagging IAB by an angle of 120 degrees. So let's say it comes somewhere here, and the current ICA again by displaced by 120 degree from IBC. So what I have written is IA is what IBC minus ICA. So if I draw the phasor corresponding to minus ICA, so this is IBC and this is minus ICA, the resultant of these phasor will give me IA, the line current IA. And since we see that this angle is 30, or the angle that exists between IBC and ICA is 60, and applying the same thing that we did for finding voltage from the phasor, the resultant of the phasors for the previous case star connected, so we'll obtain the same relation that IA will be equal to under root IBC square plus ICA square plus IBC ICA cos of 60 degree, and then we'll come to the conclusion that IA comes out to be equal to root 3 the magnitude of IBC, if this is IP, and IA is what is the line current. So for a delta connected system, we see that the phase voltages and line voltages are equal, so VL and AB are equal. This is what we wrote first, and the relation that exists between line current and phase current is given by this expression. So line current comes out to be equal to root 3 times of IP. And likewise you can obtain relations for other line currents as well, so I leave this upon you. So IB and IC can also be obtained, and analysis can be done in the similar way. So you will come that you will come with the same expression, IL equal to root 3 IP, and the angle, as I told you, that if you once know what load is connected, so if you know that what is ZAB or Z1, Z2, Z3, so if you know what values of load is connected in this circuit, then you can easily find the angle theta, and thus you can find the angle this IA makes with the reference. So this can be understood by problems that we might be solving in our next lecture. And there is one more thing that is left, and that is power for the three-phase system in both star and delta connected. So that will again be taken in the next lecture. And before that, if you have any questions or doubts, you can post your questions or mail me, or you can ask me during our live interaction.